Hello, this is Calculus 1, MAT221. This is the applications of the derivative. This is section 4.3, talking about the derivative and the shapes of curves, talking about the first and the second derivative tests. So what do we know about, what does the derivative tell us about the graph of a function and the function itself? We know from Unit 2 and what we've done in Unit 3 that if the first derivative is positive, then the curve will increase. When the first derivative is negative, then the curve is decreasing, and vice versa. When the curve is decreasing, the derivative is negative. When the curve is increasing, the derivative is positive. If the second derivative is positive, then the first derivative is increasing and the original curve will be concave up. And if the second derivative is negative, then that tells us that the first derivative is decreasing and the original curve was concave down. This is stuff that we looked at in Unit 2, and then we looked a little bit more about it in Unit 3. So we also know if the first derivative is positive, the curve is rising. When the first derivative is negative, the curve is falling. When the first derivative is 0, we have possible extrema. We have critical points, which we did in the last section. We talked about critical points. That's when the first derivative is equal to 0. These are possible local maximums or minimums. Now remember in section 4.2, we talked about that a function can have a critical point but not be an extreme. So we say they're possible local maximums or minimums, and most of the time they are. But every once in a while we'll have a critical point or a critical value where the derivative is not an extreme. We also know that the second derivative is positive. It's telling us the curve is concave up. When the second derivative is negative, the curve is concave down. And when the second derivative is 0, these will give me possible points of inflection. This is possibly where the original curve has a change in its concavity, or there's a possible point of inflection. All right, so noting these things, if I asked you to sketch this curve without a calculator or a computer, how could we do this using calculus? Now, for the most part, we can use calculators or computers to do this, but I'm going to use a relatively simple example to start, and then we're going to use the process and the ideas and the analysis behind this simple equation to look at other equations and using calculators or computers. But right now, let's look by hand. So since this graph is a positive cubic, we would expect the graph to be S-shaped, increasing, then decreasing, then increasing again. But where exactly does the curve turn and what is the shape, or where's the concavity of the graph? Well, the graph actually looks something like this. But how could we use calculus to do the analysis? We could use the derivative and look to see where the critical points of this function is by looking at where the first derivative is equal to 0. So let's determine the nature of f of x by looking at the derivative. First, we find the points where the derivative is equal to 0. Remember, these were called critical points. If the derivative is going to change sign around these points, we know that the function must be changing direction. These points can tell us even more about the original function. We notice that if the derivative of the function changes sign from positive to negative, in other words, if the function is increasing, then decreasing around the critical point, then the function must have a local maximum there. If the derivative function changes sign from negative to positive around a critical point, then the function must have a local minimum at that critical point. These are the facts that give us what's called the first derivative test for local extrema, or for short, the FDT, the first derivative test. So how do we test for local extrema, for local minimums and maximums, using this thing called the first derivative test? So what we do is, suppose P is a critical point of a continuous function, f of x. So again, we're talking about a continuous function. If the derivative changes sign from negative to positive around this critical point, then the function f of x must have a local minimum at that critical point of P. If the derivative changes sign from positive to negative around that critical point, then the original function f of x must have had a local maximum point at that critical point of P. And you can see it from these values here. Notice here, if the derivative is negative on one side, and then the derivative is equal to 0, and then the derivative is positive on the other side, you can see that the curve must have had a local minimum point. If the derivative was positive on one side of a critical point, then 0 at the critical point where the horizontal tangent line exists, and then the derivative was negative on the other side, you can definitely see that that would have been a local maximum. This is the first derivative test for local extrema, looking to see where the first derivative changes sign. So, if I said to you, here's the graph, if we looked at the graph of y equals x cubed minus 3x squared plus 4, and by the way, I factored this cubic for you, so it's a fact, this is the factored form. You can see by the factored form there's a multiplicity root here at x equals 2 and another root at x equals negative 1. We knew that from pre-calculus. Let's go through these procedures. Let's find the first derivative. So the first derivative of this function is relatively easy. It is 3x squared minus 6x. Let's set this derivative equal to 0 to find the possible critical points. We noted that this derivative will never be undefined because it is a quadratic. Setting this equal to 0, we get x squared minus 2x equals 0, or x equals 0 and x equals 2. X equals 0 and x equals 2 are the locations of the critical points of this function. They are locations of possible points of maximums or minimum points, possible points of extremes. So we possibly have an extreme at x equals 0 and x equals 2. And because this function is defined on the domain interval from negative infinity to infinity, we will only have local extremes here. We will not have global extremes. So what we do is we organize our thoughts into some sort of a chart. So we make a chart. And we do the first derivative test here. So the first thing we do is on the chart, we put the critical point at 0. And we look, well, we know the derivative there is equal to 0. Then we pick a point on either side of these critical points. So in this case, x equals 1 is between the two critical points at x equals 0 and x equals 2. Now, unlike what we did with the extreme value theorem in section 4.2, here with the first derivative test, what we do is we look at the sign of the derivative between the critical points. Now notice we're looking at the sign of the derivative, not the original function, but the sign of the derivative. So the sign of the derivative, by putting this in here, if I put in 1, I get negative 3. So that tells me in this area between the critical points, the derivative is negative. Now we pick another point on either side of these critical points. I'm going to pick a point over here at negative 1. So notice the critical points break up the region of the function for functions below 0, for values between 0 and 2, and for values greater than 2. So let's look over here. I just picked an easy number. I picked in negative 1. I put it into the derivative. Here the derivative is positive. And then I pick another point on this third region greater than 2, where my domain region is greater than 2 on this side of the critical point of 2. I pick 3. You could pick any point, by the way, greater than 2. Here we see the derivative is positive. Okay, so what does the first derivative test say? The first derivative test says that if I have critical points, okay, I have 2 critical points. One is at 0, one is at 2, x equals 2. And if the derivative changes sign around the critical point from positive to negative, That's telling me that the curve is rising, then horizontal, then falling down. So rising, horizontal, decreasing. That means this critical point must locate a local maximum. Let's look at the other critical point. On one side, on the left side of the critical point, we have the derivative is negative, which means the curve is falling. Then we have the derivative is 0, which means the curve is horizontal. Then the derivative is positive, which means the curve is increasing. So the curve is falling, then horizontal, then increasing. That locates a local minimum. So I have a maximum value occurring at x equals 0. I have a local minimum value occurring at x equals 2. Note, it is not sufficient to simply draw a chart and then write your answer. You must actually explain what the first derivative test is telling us. So in a full sentence, there is a local maximum at the point 0, 4. Now again, where did I get the 4 from? I took 0 and put it back up into the original function to get the output of the function when my input was 0. So there's a local maximum at the point 0, 4 because the first derivative is positive for all x from negative infinity to 0, and then negative for all x from 0 to 2. That means we have a critical point at x equals 0. The derivative is changing sign from positive to negative around that critical point, therefore causing a local maximum. Likewise, there's a local minimum at x equals 2, 0. Again, where did I find this? I went and took the input of 2 back into the original function, and you can actually see it here. When I put in 2, I get a 0 for my output of my function. So when x is equal to 2, the output of the function is 0. This is a local minimum because the first derivative is negative on one side of the critical point, positive on the other side of the critical point. Therefore, that critical point must be locating a local minimum value. All right, I'm going to stop my video here before I get into the second derivative test for local extrema because I don't want them to be confused. So you can stop your video and go through a couple more examples here before we get to the second derivative test.